Good morning. Welcome to our webinar, Which Column Dimension and Particle Size Are Best for Me? Thank you for joining us today. We especially appreciate your attendance right now while many of us are struggling to balance professional and personal needs. We hope you all stay safe and healthy. My name is Tracy Hartledge. I'm a sales representative and project coordinator for Chiral Technologies and will be your moderator for today's session. Presenting today's webinar is Dr. Weston Umstead, Manager of Technology here at Chiral Technologies. Please note that during the webinar, you will have the ability to submit your questions as they arise. Please take a look at the control panel on the right side of your screen and click on the Questions tab to begin. Fielding your questions today will be Bill Watts, a member of our technical team. We have placed a copy of today's presentation along with two other useful documents, an application note, and our product list. They are available in the handout section of the control panel. I now turn the microphone over to Dr. Umstead. Wes, the floor is yours.
All right, thank you very much, Tracy, and thank you again to everybody who is out there listening today. We appreciate you taking the time, given the uncertainty that we're all facing right now, to tune in and learn a little bit about what column dimension and particle size are best for me. This is a question that we often get asked by customers, both new and more advanced, especially when somebody is looking to begin starting a screening setup, for instance, and exactly how they should begin the process, what column dimension, particle size, etc. So that's going to be a focus today. As a brief overview of the topics that we're going to touch upon, I want to start off with just a product overview, what CSPs, chiral stationary phases we offer, what column dimensions and what particle sizes we offer as well. Give you a little overview on that before we actually talk about the individual features of the column and what kinds of effects we can expect in changing column length and changing the column inner diameter, and then moving into particle sizes, what kind of effects we expect to see when we change particle sizes. Specifically, we'll talk about analytical versus preparative scale. That's the major focus of changing particle size typically anyway. And then we'll finish with some conclusions and some email addresses if you have questions related to your specific cases. So in the beginning of chiral chromatography, the choices were pretty straightforward as far as instrumentation was concerned. You were going to be using an HPLC with a set number of mobile phases, normal phase, polar organic mode, and reversed phase primarily. You're going to be using UV detection as your source. There is a slight difference between analytical and preparative scale methods, not necessarily in column dimension and particle size, but more optimizing the method to be able to load more material on the column to run a preparative scale separation, for instance. The most number of choices came in the form of the polysaccharide phases or the chiral stationary phases that were available. And at that point, it was only the coded phases, things like AD and OD, which you are all probably very familiar with. But now the choices have expounded quite dramatically. And for the purposes of our discussion today, as the title of the webinar indicated, we will be focusing in strictly on column dimensions and the particle size offerings that we have and where they all fit into the different applications that you might be looking to use them in. To talk about the chiral selectors first, we'll focus on the polysaccharide phases, which are kind of our bellywick. We have the Chiral Pack line of columns. Chiral Pack encompasses all of our coated amylose as well as our entire line of immobilized columns. And then we also have our chiral cell line, which is the coated cellulose phases. So our first generation coated columns were all of the phases that you're probably very familiar with, things like AD all the way through OZ. And then we have our second generation immobilized columns, which are compatible with the normal phase, polar organic, reversed phase, and SFC conditions that the first generation coated columns were compatible with, except now you can also use them with what we call the forbidden normal phase solvents, things that contain dichloromethane or ethyl acetate or THF. And then we have our specialty selectors, our protein columns, ligand exchange, crown ether, Lindner, and zwitterionic Zwick's phase. And these are all available in a wide variety of different column dimensions, and in some cases, a wide variety of particle sizes as well. So what we offer as far as column dimension options goes, if we look at just column lengths for analytical columns, everywhere from 50 millimeter, 100 millimeter, 150 millimeter, and 250 millimeter length, and for preparative scale, 150 millimeter length, 250, as well as a larger 500 millimeter length column. For column inner diameters, which I will most likely be referring to as ID from here on out, for analytical columns, we're looking at 2.1, 3, and 4.6 millimeter IDs. And for preparative scale, anything from 10, 20, 30, 50, all the way up to a 100 millimeter length or 100 millimeter ID column. And particle sizes, I broke down into analytical versus preparative scale. Analytical only, we're looking primarily at 3 micron, although we can also use our newest line of sub 2 micron columns that have been optimized specifically for UHPLC. It's not that you can't use the sub 2 micron columns on a normal HPLC. However, you generally won't see the added benefits, reduction in extra column band broadening, for instance, that you would see using them on a UHPLC, but they can certainly be used on HPLC as well. For analytical and preparative scale, I have 5 micron in here. 5 micron is very interesting in that it kind of straddles the line between, straddles the line between both analytical and preparative scale. Oftentimes, if a user knows that they're going to be scaling up to preparative, to a preparative separation, they will perform their analytical work on a 5 micron column because there's no unexpected changes in terms of the resolution of the chromatography when you go to preparative scale. And then for preparative only, we have 10 micron to 20 micron. Back in the days of the origins of chirochromatography, 10 micron was the go-to for analytical as well. However, that was because 10 micron was really the only particle size that was available. Now we pretty much relegate it only to preparative scale, and if there are any methods out there on 10 micron, we usually advise that you switch over to 5 micron at a minimum, and of course 3 will get you the extra resolution that you might be looking for. All right, so if we move into our section on the discussions of column dimensions and things that you can expect to see when you begin changing column length, for instance, the obvious change that you're going to see in increasing the column length is an increase in resolution. I think most of us are probably very familiar with that. However, we're also probably aware that it's not a direct one-to-one proportionality, meaning that if you increase the column length by twofold, you will not see a twofold increase in the resolution. Instead, the resolution increases by the square root of n, where n is the number of theoretical plates. And so if we look at the resolution equation here, that's pretty well laid out. So if you increase the column length by twofold, you should, in theory, see an increase in the number of theoretical plates by 2 as well. So number of theoretical plates is directly related to the column length. In theory, I said, in practice, that's not always the case, although it is usually very close to that. So if we increase the column length by 2 and therefore increase the number of theoretical plates by 2, we should see an increase in resolution by the square root of 2, or 1.4 in this case. And if we increase it by 3, we should see an increase in resolution of 1.7. If we look at an actual separation to kind of prove that out, this is a separation on ChiroPack IC3. In green here is a separation on a 50 millimeter length column, and the resolution was 1.33. If we increase the length by 3 to a 150 millimeter length column, and we calculate the resolution is 2.29, which is not quite 1.7, it's actually slightly higher. But as I pointed out, in theory, you will see a 1.7 fold increase in resolution, but there is some variability, obviously, in moving to a different column. The number of theoretical plates is not going to be exactly 3 times more. There's always going to be slight variability in the conditions when you actually run it, temperature, and so forth, things that can ultimately affect slightly the resolution. But the point of this example is to show that the rule more or less holds true in practice as well as in theory. What about the retention time? Obviously, if you increase the column length, you should expect to see an increase in the retention time. And in this case, it is one-to-one proportional. So if you were to increase your column length by threefold, you should expect to see an increase in the retention time of threefold as well, assuming, of course, that all other conditions remain the same, such as flow rate, temperature, mobile phase composition, etc. Now, if we go back and we look at that example again of the separation on ChiralPack IC, you can kind of estimate well from these chromatograms what the T1 and T2 of the peaks are, but I broke them out into a separate table to make the visualization a little easier. So you'll see here for the 50 millimeter length column, T1 is roughly 1.3 minutes and T2 is roughly 1.5 minutes. If you bump it up to the 150, then you do see actually a straightforward threefold increase in the retention time, slightly off for T2, but again, that's kind of potentially coming from differences in the column packing and the effect that the resolution has on the overall separation. So what does changing the column length not affect? So changing the column length, increasing it, does not affect the retention factor or the capacity factor. The retention factor is a measure of how retained a compound is on the column, as shown by this equation here, where K, the retention factor, is equal to TR, the retention time of the peak, minus the T0, or the dead volume, the unretained volume on the column, divided by T0. And so although you are increasing the column length and therefore you're also increasing the analyte retention time, the column void volume is also increasing proportionally. So if we go and we look at the actual void time or the void volume of a given column for a 50 millimeter length column flowing at 1 milliminute, that time is approximately 0.55 minutes. And for a 150 millimeter length column, that's somewhere in the neighborhood of 1.6 minutes. So if we go and we plug those numbers into our equation for K and we use the TRs from the previous chromatogram, you see here that for the most part, K1 and K2 are roughly the same between the two columns. There's, again, some slight variation, partially in my estimations of the retention times, and also, again, coming from the slight differences in the variations in the column packing and so forth. But the proof is, in theory and in practice, that they're roughly the same, at least close enough to where you can't say that there's a significant enough difference. What else does changing column length not affect? It does not affect the selectivity. Selectivity is a measure of a system, in our case, a chromatographic system, to distinguish between enantiomers. And as you can see, the equation here for alpha for selectivity is essentially just the ratio of the retention factors. And so because selectivity is a ratio of retention factors, it should be similar. It should not be changing as you increase the column length. So to prove that out, here is that same example again, and calculating the alpha values based on the previous table. You see here that, again, the alpha values are very close to each other, differences arising from differences in column packing and so forth. Now, if we move on from column length to column inner diameter, there's a number of things that we can expect to see, assuming that we keep the flow rate constant. If we go from a 4.6 to a 3 to a 2.1, flow rate remains at 1 milliminute, for instance. Decreasing the column ID will obviously increase the column back pressure. It will increase the peak height, will decrease the column loading, the retention time, and solvent use. Now, I have a little bit of a caveat to that. because again, I said this is assuming the flow rate stays the same, but in practice, we oftentimes will scale the flow rate in order to equalize the pressure, and we'll discuss that a little bit later on. But for now, imagine a scenario where the flow rate stays the same across these different IDs. So if we look just at column pressure, decreasing the column ID will increase the column pressure, again, assuming everything stays the same. If we look at our equation for change in pressure in the chromatographic system, it is directly related to the viscosity, the flow rate, and the length, and inversely proportional to the specific permeability, the particle diameter, and for our current topic, the column radius. So obviously increasing the, a decrease in the column radius or the column diameter will increase the pressure. So if we assume, again, that flow rate is 1 mil a minute for all of these 3 analytical ID columns, same particle size, same mobile phase composition, same column length, what we would expect to see is an increase in the pressure of the equation that I have shown here, where radius 1 divided by radius 2 squared should give you the rough estimation or translation of what the new pressure would be on the new column. Now, because of some pressure limitations, not only with the columns, but with the systems, not all of this data was actually gathered in the lab, but for instructive purposes, you can see basically what you would see if you were able to achieve this, looking just at your 4.6 millimeter ID columns on a 50 millimeter length. Estimation at 30 bar, you would see 71 bar and 144 bar on the same length, but a decrease in the column inner diameter, and so forth down the line here. Now, I talked about scaling before, because if you see here, especially this corner, you're starting to achieve pressures that are not only incompatible with the column, but incompatible with most HPL systems as well. So in order to counteract that, like I said, what we often practice is flow rate scaling. So flow rate can be scaled to equalize the pressure, and to do so for a 4.6 millimeter ID column flowing at 1 mil a minute, the corresponding flow rate for a 3 millimeter ID column would be approximately 0.43 mils a minute, and for a 2.1 millimeter ID column, roughly 0.21 mils a minute. Now, equalizing the flow rate is going to have some other effects down the line. Obviously, your retention times are going to be more or less the same, solvent use and things like that. So if we go back to keeping everything the same, and we look at keeping the flow rate the same, if we move into those narrower bore columns going from 4.6 to 2.1, for instance, all of these columns have obviously a smaller inner column volume, and therefore will experience less column broadening. So as the analyte is moving through the column, less space for diffusion, and therefore as the peaks are coming out of the column and into the detector, they will appear sharper as a result of that decrease in diffusion. This can be particularly helpful when you have methods that require high sensitivity to especially low level impurities. So for instance, if you're trying to quantify a 0.01% impurity and it's eluting late on the tail of your major impurity, it's certainly beneficial to ensure that the peak height is relatively high and not diffuse. It makes it easier to do your quantifying than it would be if obviously things were broadened out or starting to tail or co-elute into the peak that was coming before it. If we, again, make sure that we keep the flow rate the same and we're just decreasing the column ID, we will expect to see a decrease column loading, decrease in retention time, and a decrease in solvent use as well. So decreasing the inner column volume means there's going to be less volume for packing material. And because there's less packing material, basically it's easier to overwhelm the selector sites. So you need to inject less sample, which can be helpful, obviously, if you are trying to conserve a valuable, precious sample, but less sample needed, either a smaller injection volume or a lower concentration in order to maintain the performance. Retention is decreased if the flow rate is maintained, meaning if you have a 4.6 millimeter ID column at 1 milliminute and you flow it on a 3 millimeter column at 1 milliminute, you will have obviously less retention. But it will be equalized, as I mentioned before, if the flow rates are scaled proportionally, or at least close to being equalized. And then there's a decrease in inner column volume by going to those smaller ID columns. And if you're reducing the flow rate at the same time, you're obviously going to be using less solvent. So for screening, for separations that involve a harsher, environmentally unfriendly solvents like dichloromethane or chloroform, this obviously gives a little bit of an advantage in that regard. All right, so let's move on to talking about particle sizes and changing particle sizes. We started the column dimensions off with resolution, so we'll start particle sizes off with resolution as well. So if we decrease our particle size, we should expect to see an increase in resolution. The improvements in packing efficiency result in an increase in the column efficiency. By that I mean smaller particles pack more efficiently than larger particles do. And because smaller particles pack more efficiently, we will see an increase in the number of theoretical plates n. And as we talked about before with column dimensions and length, an increase in n results in an increase in resolution by the square root of n. As an example of that, here is a chiral pack IB3, so a 3 micron column, and compared to a chiral pack IBU, sub 2 micron, 1.6 micron column. Same column dimensions, so a 3 by 100 millimeter length column. If we were to pack the column and simply calculate the number of theoretical plates for chiral pack IB3, here you see that the number of theoretical plates is just a little north of 15,500. And for chiral pack IBU, it is almost 23,000. So there's an increase in the number of theoretical plates of almost 1.5. And that again has everything to do with the fact that these particles pack more efficiently, and therefore you have an increase in the number of theoretical plates. Going back to what we talked about in terms of improvements in resolution, the square root of 1.5 is 1.2, and so you do see roughly a 1.2 fold increase in resolution from 7.4 to 8.8. Now, to dig a little bit deeper, we can look at a Van Dienter equation to figure out what exactly is going on here. So we know that if we have a higher number of theoretical plates, we have an improvement in resolution. We also know that smaller particles pack more efficiently. So for the purposes of this discussion, we can focus in just on the A term, eddy diffusion, and the C term, resistance to mass transfer, as those are the terms that are directly affected by column packing and particle size. So eddy diffusion, A term, basically just describes the path at which the analyte has to travel through the column. That is shortened by a smaller particle. And the resistance to mass transfer is the way in which we describe the ability of an analyte to interact with the stationary phase and then come back off of that stationary phase. And the C term is diminished or decreased anyway for smaller particles. It's easier to interact and come back off of a smaller particle. Now you can see based on the shapes here of our Van Dienter equation that the A term basically sets the overall minimum of our plate height here. So if we have smaller particles, we would expect a smaller plate height. And the C term, the resistance to mass transfer, the slope of this line is shallower for smaller particles, meaning that as we increase our linear velocity of our mobile phase, we should expect to see a diminished loss of resolution. So in practice, if we look at what that looks like here, a Van Dienter plot of 10 micron, 5, 3, and 1.9 micron particles, the effect of the A term, as you can see here, for 10 micron, because you can't pack as efficient of a column in larger particles, has a plate height of somewhere around 0.02 millimeters, whereas your 1.9 more easily packed particles is well below 0.01. And of course, as we increase our linear velocity, we do see that expected loss of resolution for 10 micron and even 5 micron, whereas 1.9 is more or less relatively flat. So that's kind of why we can get the improvements in resolution with our smaller particles going faster, whereas we generally tend to lose that with our large particles. So if we look at pressure for a second here, as particle sizes decrease, pressure increases, assuming again that all other parameters are maintained. So going back to that pressure equation, we know that the change in pressure is inversely proportional to the particle diameter, so that all holds true. This, of course, can be counteracted by decreasing the column length or decreasing the flow rate, which we talked about previously when we talked about scaling for flow rates. Now, because we know we can push our columns, our small particle sizes faster and not lose any resolution, it allows us to generate something that looks something like this, where we might have had an older separation on a 5 micron chiral pack IA. The column dimensions here are 3 by 150. The resolution is certainly very good here. The flow rate is very modest as well, 0.425 mils a minute. Obviously, this could be increased, the flow rate could be increased, and we could probably shorten this analysis time a bit. However, keeping in mind what the Van Diemter curve looks like, we might also find a situation where we begin to lose resolution as a result of increasing that speed. But if we move down to a smaller particle size, 3 micron, for instance, here we can push them a little bit faster and not have any issues or less of an issue with pressure. So we can cut down our analysis time to 4 minutes. And of course, as we decrease the particle size, we're going to see an increase in the pressure. So we can also reduce our overall column length to a 100 millimeter length column, which will have an effect on retention time as well. And then take it a step further and move to our sub 2 micron columns. Here now, we really aren't expecting a whole lot of loss in resolution at all if we really increase the flow rate. So we're up to now 1.7 mils a minute. We have our retention time down to less than a minute, and we obviously have no loss in terms of the resolution, but we've saved ourselves a substantial amount of time, a substantial amount of solvent as well. This is extremely important, especially when you're looking for high throughput screening. So this is an example of a 7 compound library on 5 sub 2 micron columns. This is a screening that could be done in the course of 4.5 hours versus what traditionally had been done on 3 or even 5 micron columns, which would have taken at least overnight, maybe even into the next day to get these results back. So it's a huge time savings, especially when you're trying to screen as many columns as you possibly can, or as many compounds as you possibly can in one time. We talked about sample loading before. So sample loading, obviously smaller particles have less surface area, and so they can naturally only handle smaller injection volumes. So we would never be doing any kind of an analytical or any kind of a preparative separation on sub 2 micron or 3 micron particles. It just simply is way too inefficient. We would need to at least use 5 micron, maybe even 20 micron, depending on the scale. So larger particles and therefore larger column dimensions are much more appropriate for preparative scale chromatography. Now, back at the very beginning of the presentation, I mentioned that 5 micron kind of straddles this very interesting line where it's useful for both analytical and preparative scale. And what we see a lot of times happen is customers will develop methods on 4.6 by 250 millimeter length, 5 micron analytical columns. And what they will do is they know that it translates well into preparative columns based on these scaling factors that I have shown here, a 4.6 millimeter ID column to a 1, 2, 3, or 5 centimeter ID prep column of the same length, easily scales. And if you perform a loading study to determine the productivity in either milligrams or grams of material processed per hour, you can figure out what your loading is on your analytical column and then gauge pretty accurately what size column you need for the preparative scale separation that you're planning on doing. And so if we do what is called the touching band approach, we would perform an analytical injection such as this for this precursor of a calcium sensitizing drug. Very nice looking analytical injection. We would begin increasing the injection volume and we would achieve something that looks something like this, where in red is the most concentrated or the highest volume injection that we're making. It's roughly 20 milligrams of material on the column. And what we see here is obviously the tail of peak 1 is slowly approaching the front of peak 2. We might even be able to load more material on the column in this case, but it demonstrates the point that we're loading more and more and more on the column. And so we can calculate our productivity and figure out, especially if you're buying a new column, what size do I need given the scale that I'm trying to separate. All right, and lastly here, we'll finish with our conclusions. We're almost out of time. So what should I choose? Up to this point, we've basically just been talking theory, but in practice, the question is what column dimension, what column particle size should I be using for my separations? Now, these recommendations that I'm going to make you are not hard and fast. They are what we internally do and what collectively as the DiCel community we've established. But for your given separation, you might find that you can get away with a smaller length, a shorter length, or a smaller ID, or a smaller particle size. It really depends on your separation. But in practice, what we recommend for analytical HPLC, typically, we're going to be utilizing a 4.6 millimeter ID column of either 150 or 250 millimeter length. And as far as particle size goes, either sub 2 micron or 3 micron. Now for the sub 2 micron columns, as I have marked here, they are currently only available in 3 millimeter ID and limited to either 50 or 100 millimeter length columns. Not that big of a deal, but something to be aware of. We can custom pack longer length columns if you so choose, but that's what is more or less commercially available at the moment. Now, again, like I said, this can change. This really depends on your separations. 5 micron, as I mentioned, is certainly useful if you're planning on transitioning to preparative scale. But if you're just looking for analytical only, then 3 micron is a good way to go. For faster screening, you can certainly look at doing a 50 millimeter length column, but there is a higher likelihood that you might miss a separation if you go that direction. So when we do our screening internally, generally, we're always screening on a 150 millimeter length column just to kind of minimize the chances of us missing something. For prep HPLC, as far as utility goes, most people are utilizing either 2 or 3 centimeter ID columns of 250 millimeter length. Particle sizes for HPLC, either 5 micron or 20 micron, depending on the scale. Most people don't use 10 micron anymore. You can get away with 5 or 20. Both of them kind of serve the role that 10 micron used to. We can use a 150 millimeter length column if you are operating near or at the system pressure limits and you have concerns about potentially going over pressure. Obviously, decreasing the column length will help with that issue, but you might have to do some optimization, obviously, in going to a shorter column. For SFC, for analytical SFC, typically you're utilizing either a 3 or a 4.6 millimeter ID column of either 100 millimeter or 150 millimeter length. Again, that doesn't mean that you can't use a 250, but generally speaking, most people are screening, especially with 100 or 150 millimeter length. Particle sizes are the same, either sub 2 micron or 3 micron, and 5 micron if you're planning on doing any preparative scale work. For faster screening, you can, again, get away with a 50 millimeter length, but you might miss a separation possibly. For prep SFC, same length, I should say, 250 millimeter, and same column IDs 2 or 3 millimeter. Particle size, though, is typically only 5 micron. 20 micron does not get used very often for SFC separations. Generally, it doesn't need to be, because you have a lower viscosity of your mobile phase. Even though you would expect higher pressure on 5 micron, generally it's mitigated by the fact that your viscosity of your mobile phase is much less. And again, you can use 150 millimeter length column if you're operating close to system pressure, but it's not necessary and could potentially require some optimization. Well, that is all I have for you today. It was a very brief discussion, I know. So if there are other questions that you have related to this issue, or like I said at the beginning, if you have specific questions about your separation that you'd like us to help you with, feel free to email us at questions@cti.dicel.com for general column chromatography or method development questions. Feel free to email me directly about this presentation or about any chromatography or column questions that you might have as well. I do monitor the questions email address, so chances are I will see a question either way. We do have a number of webinars that we've done in the past. We have a chiral method development, a sub 2 micron column care, and method validation series that we've performed. And we have 2 more coming up this year. one in July, one in November. The topics are currently to be determined, but one of them will probably be a repeat of the chiral method development talk that we gave previously. But we're always open to your suggestions, so feel free to shoot us an email and let us know what topics are interesting to you and what you might want to see us discuss further. At this point, I have nothing else for you, so I would like to thank you again for tuning in today. We really appreciate your attention. We're always looking forward to helping you as much as we possibly can. So please don't hesitate to contact myself or questions or your sales rep, and they'd be happy to help you in any way that we can. For myself and from the rest of the Dicel family, especially here at Chiral Technologies, we wish you and your family the safety over the next few weeks and months as everything begins to develop here in our country. Let us know how we can help in any way. And again, we appreciate your time today. So stay safe out there, and we will see you next time.